Hi, in this lecture video, I will continue to discuss electron stability by focusing on the resonant effects, the inductive effects, and the orbital effects. So first, let's discuss resonance. How the resonance affects stability. So some molecules, but not all, some molecules are able to produce multiple resonance structures. And this basically means that those molecules are able to distribute or spread out the electron within that molecule. And that can then reduce the buildup of electron in any one particular atom, and therefore make the electron not as dense and therefore more stable. So the more resonance structure that a molecule can make, the more stable that electron will be. Now let's take a look at an example. So here we have ethoxide, and in the case of ethoxide cannot form resonance structure. And we can see that here it has electron on this oxygen. So let's put in this 3 lone pair electron. So it will be complete octet. And we can then see here in this case right here, all this negative charge and all of this lone pair electron right here locate on this oxygen only. And this oxygen or this molecule is not able to distribute the electron to any other atom in the molecule, because this cannot form any other resonance structure. So as shown here by the electrostatic potential map, that this oxygen right here has a very high buildup of electron density. And therefore we can then see that this species right here is not as stable. And again, we can see that the charge, so we would say that the charge is localized or locate on one single atom only. And in this case, it is the oxygen. And now let's compare this to acetate. So in acetate, we have this negative charge right here on this oxygen, very similar to the other oxygen in ethoxide. But now the difference with this oxygen right here in acetate is that it is able to actually form resonance and donate an electron to the other oxygen. And this is how it will be able to produce resonance structure. So this electron is donated in to form the double bond between this oxygen and this carbon. And this pi electron is then broken, and now the pi electron go to the oxygen as the lone pair. And the structure of the other resonance structure would then be as follows. And what this is telling us is that in these two different structures here, these are two different ways how this molecule can distribute an electron. In one instant on the left, electron locate on the oxygen on the bottom. And now 50% of the time, the oxygen then locate on the other oxygen on top. But then basically mean that this molecule is able to distribute an electron between these two oxygen atoms right here. So therefore, the electron density on each of the oxygen would then be reduced compared to the oxygen in ethoxide. And as the electrostatic potential map is showing, that now we can see both of this oxygen right here, and they have electron build up on them, but not as dense compared to the oxygen in the case of ethoxide. So you can see that this electron right here is then said to be more delocalized. So the charge of the electron is delocalized over two atoms, or distributed over two atoms, and therefore it is more stable. So that's how resonance can actually affect the stability of a molecule. And now next one, the induction or the inductive effects. So the induction and the inductive effect has to do with electronegativity. So whenever we have a molecule with atom with different electronegativity in them, this would then create a polarized region whether one part of the molecule would then become partially positive and the other part become negative in the molecule. And due to the formation of this partial positive and partial negative, this partial positive and negative right here can then stabilize a negative charge or a positive charge that are in close proximity to it. And therefore that stabilize the negative or the positive charge. So a partial positive charge can inductively withdraw electron density from a negative charge if the negative charge is close by to it, and therefore stabilizing that negative charge. And now let's take an example right here in this case. So in this case right here, we have a negative charge on this oxygen, and in this case the same thing. But now on the case on the left, there's no inductive effects because there's no other atom. Compared to what we are focusing in here, there's no other group in here have an atom of difference or big difference in electronegativity. So this has no inductive effects. But now for the molecule on the right side, so there are these 3 chlorine right here connected to this carbon, and because the carbon it has a much lower electronegativity compared to the chlorine, so this chlorine right here is inductively withdrawn electron from this carbon right here, and all 3 of them do. And as a consequence, that would then make this carbon right here become very positively positive. And when this carbon right here is positively positive, it can then stabilize a negative charge that is close by to it. So in a way, this is how it can neutralize this negative charge, and that makes this more stable. So in this case, this molecule E has benefited from the inductive effects, and therefore it is more stable. So that's what the inductive effect is. And lastly, the orbital. So depending on which orbital that the electron locate in, they can have different stability to them. And the reason why is that different orbital have different size and shape to them. And the electron located in them can also be different. So in electron, in orbital that are closer to the positively charged nucleus are then more stable. Now, here in this class right here, we're dealing with the carbon a whole lot, and we have seen the differences between an sp3, sp2, sp2, and sp1 carbon already. So dependent on the electrons and which of this orbital that they locate in, they actually have different stability to them. For example, so here will be the size and the shape and the length of the orbital. We can then see that the sp3 orbital is longer. So that means the electron, if we were to have electron in an sp3 orbital, it will then further from the nucleus compared to the electrons that locate in an sp orbital, because basically the node right here in the middle, and that's where the nucleus would be. So in the case of an sp1 atom, then now electron located in the sp orbital would then be much closer to the nucleus, and the nucleus is then positive, and that helps stabilize the electrons because electrons are negatively charged. So that's how orbital can actually affect or have different stability to them. So here's an example right here. So in this case right here, we have this molecule with the carbon being negative here, and the other molecule where the carbon is negative over here. So we will then see that this lone pair of electron right here, or the hybridization of this carbon, is that it is sp2. And the electron here, the lone pair of electron, actually locate on an sp2 orbital. Versus over here, this carbon right here has sp1 hybridization, and the lone pair of electron actually locate on the sp1 orbital. And because this locate on sp1 versus locate on sp2, this lone pair of electron right here, it actually come closer to the nucleus of the carbon compared to the other lone pair. And that basically make this one right here more stable, because electrons is in the sp1 orbital, and therefore it is more stable. So that the effects of orbitals on electron stability.